Hello everyone, my name is Pradeep. I am a development manager at MathWorks. Are you facing challenges in partitioning control algorithm for multi-core MCUs for motor control application to achieve higher performance? If yes, then I'm going to show you how you can use SoC Blockset to partition real-time motor control application to run on multiple cores and analyze the higher PWM frequency effect on controller performance in simulation phase, and then verify the tuned controller on the hardware. SoC Blockset enables model-based design for multi-core microcontrollers based application development. It provides multi-core architecture modeling with IPC communication, out-of-the-box support for programming multi-core MCUs like TI F28379D, guided deployment workflow using SoC Builder app. I am using a C2000 Delfino MCU F28379D LaunchPad development kit to verify the behavior on the hardware. Here we see a Simulink model that represents the motor control closed loop system. This model simulates dual core motor controller for a permanent magnet synchronous motor inverter system. Task Manager block highlighted in green simulates the execution of software tasks as they would be expected to behave on an MCU. The task manager executes individual tasks based on their parameters such as period, duration, trigger, priority, or processor core, and the combination of that task with the state of other tasks and their priorities in the running model. Tasks can be timer driven or event driven. Inside a single reference model block, the timer driven tasks are represented as rates and the event driven tasks are represented as function called subsystems. Multi-core model contains at least two task manager blocks, each connected to a model reference block, representing the process to be run on a separate core. The controller subsystems highlighted in green represents the partition algorithms running on different cores. The current control is running on core 2 and the speed control and position estimation is running on core 1 respectively. The blocks highlighted in green color represents the inter-processor communication data channel using which processors can communicate to each other asynchronously. Inter-processor communication consists of the data write, data channel, and data read blocks. The inter-process data write block asynchronously sends message to another processor in an SoC using an inter-process data channel. The inter-process data channel block provides a channel for asynchronous data transfer between two processors. The inter-process data read block asynchronously receives messages from another processor in an SoC using an inter-process data channel. Now let's see the model configuration for multi-core architecture. Click on the System on Chip tab and then click Hardware Settings to open the Configuration Parameters window. In the Hardware Implementation tab, the processing unit parameter is configured to none, indicating that it is the top level system model. Now let's open one of the referenced model within the system model to see how it is configured to run on a specific core. In the Hardware Implementation tab of referenced model, the processing unit parameter is configured to C28X CPU1, indicating that it is configured for core 1. Now let's talk about how you can leverage additional cores to achieve higher loop rate by partitioning the control algorithm to run on multiple CPUs. Let's begin by looking at a problematic case where motor control algorithm is running on single core, generated PWM frequency is 40 kHz, the execution time of current loop task driven by ADC interrupt is 26 microsecond, the execution time of speed loop is 5 microsecond. Run the simulation and view the results in STI. As you can see in the picture, the speed feedback from the motor is 0, where it is expected to follow the reference speed highlighted in green color. This is because the current loop task is overrunning, leading to the drop of speed loop tasks as shown in the below graph. With 40 kHz PWM frequency, the current loop is expected to finish its execution within 25 microseconds. You can also analyze this behavior on the hardware using the task profiling capability of SoC Blockset. To address the issue with the single core model, let's partition motor control application across two cores of the TI 2000 F28379D. We partition the control algorithm by executing current control on core 2 and speed control and position estimation on core 1 respectively. Data transfer between the cores are handled by inter-process data channel block as I explained earlier. Using both cores to execute control algorithms allows us to achieve higher controller bandwidth. Now run the simulation and view the results in STI. In this figure, you can see that at 40 kHz PWM frequency, the speed feedback from the motor is tracking the reference value as expected. Now let's proceed with programming the TI Launchpad board to verify the behavior with a hardware test. Follow the instructions on the SoC Builder tool to run the model in external mode and view the results in STI. This figure shows the controller response from simulation and deployment at 25 microsecond current loop with 40 kHz PWM frequency compared with 50 microsecond current loop at 20 kHz frequency. As expected, the rise time in speed improves with faster current loop by approximately 50%. So to summarize, you can easily identify and fix the design problems in multi-core based motor control application early in the development phase using capabilities in SoC Blockset like multi-core architecture modeling with IPC communication, out-of-the-box support for programming multi-core MCUs like TI 2000 F28379D, guided deployment workflow using SoC Builder app. Thank you so much for watching. To try the example, please visit the link mentioned in the video description.